Hello all. So let's dive a bit deeper into this Langgraph and how internally it works. So firstly, I thought I'll make just conditional workflows lecture as lecture number 3, but I thought it will be right time to dive a bit deeper into it. So it's not like just using a functional API or orchestration framework. Let's go a bit internals of it. And firstly, let me motivate how this idea came to my mind to go a bit deeper into it. Okay, so we have seen in our last lecture about parallel workflows. And in parallel workflows, this was our state. We were generating a joke, story, and poem about a particular topic, and at the end, we were combining. So this was parallel workflow, and I'll just tell you again, this was the workflow that we built. Okay, so if you have noticed carefully, for example, let's consider this node. This is just taking topic as the input from the state, and it's not modifying the state at all. So this I just changed right now, but in the last class I already showed you the error of doing it. So rather what you do is something like this, that there should be joke and the math, so you return like this. But now if you think carefully, there's a problem here. How the state is appended, like updated now, because we are not updating state here at all. We are just taking state, like we are just touching state here to read but not to write. So we are not updating the state here. So how after the execution of this node, our Langgraph workflow will know, okay, this node was giving me the output for this particular key of my state. Similarly, for this node, this was returning for story and this was returning for poem, right? And this is where our thinking was wrong. So if you think like this, that okay, nodes are just directly mutating the Python dictionaries, which is nothing but our state, then you are wrong. So in LangGraph, nodes do not directly mutate. So if you can't recall, I can also go to lecture 1. So here, if you see that, okay, because I showed this, so you might have the intuition that, okay, in LangGraph, no, what node does is it just mutates the dictionary, which is this one. So it just takes two inputs, add them, and just mutate the state. Okay, like this. But actually it's not like this, and that was the purpose to make this lecture. So in fact what happens is the node runs, node emits something called writes, so it's like a read writes operation. So this writes, then there is something called as Pregel. So Pregel is nothing but Google's algorithm, which was introduced in around 2010. So Pregel is heavily used, or the idea is completely the same, or you can say it's copied from the Google Pregel's algorithm here by Langgraph. So it's nothing but a runtime. So why this runtime was needed? Because this algorithm describes a very efficient method for large scale parallel computation, especially using graphs. Okay, so Google made this algorithm specially for large scale parallel computation. And what we need in Langgraph, some large scale computations, right? At the end, we are building a graph, and also parallel workflows as well. We are building for faster speed and efficiency for our LLM workflows. And that's the reason of using this Pregel runtime, and Langgraph uses it. So again, node runs, and it's not like node just update the state. No, it's not like that. It just emits writes, and then Pregel applies those writes to channels. Now you think like, okay, there are two alien words. First is Pregel and second is channel. But I'll go deep into it and I'll connect all the dots. Just bear with me. So, and the next step reads this updated channel values. So firstly, what is Pregel? So as I said, Pregel is a runtime. So, and how it executes? It executes in three phases. So it's a plan, execution, and update phase. So, and after all these phases are finished, the updates are visible. So it's not like in the execution phase or plan phase, there is an update that is visible. Okay. The update, the final update will be visible after this, all three phases are finished, or you can say after the update phase is done. So what's the real flow? Again, the node runs, it emits something called updates, okay, or you can say writes or any updates. Then this Pregel batches that updates. Then what channel does is channel applies them. Now it will be clear what channel is. I have a detailed slide about channels. And then next step, sees this new updated values that is being updated by this channels. So this is how the entire flow works. But let's go, what is channel now? So again, let's go that, okay, any key in this Python state dictionary, that is, so this key A, this key B, or this key here, like joke, topic, story. Okay. So key in Langgraph is not just a Python dictionary key. Okay. At runtime, what it becomes a channel. So that's the definition of channel. So I'm trying to like actively put some dots so that you can connect at the end. So all these keys are nothing but at runtime the channel. So what channel does? Channel stores the value, channel accepts the updates, channel decides how updates are applied, and then different channel have different merge behaviors as well. So for example, let's say we are making a chat application, then we have to append because we need the history of the chat, right? Like what was the first message asked, right? But if we are just adding two numbers, then we don't need the previous result, right? Every time it's a new tune, every time new tune pair of numbers, and then there will be a new answer. Then we don't have to merge. So how you update is also dependent on channel, or you can say behavior of channel. So let's see again. Let's go to the code and see what happens. So firstly, plain state. What is reducer? Just ignore right now this reducer. Okay. So let's go to code. So I have made a simple, so this is simple workflow of, you can say, question answering system. I'm not using LLM just to save time here. So simple one node workflow, and it's like start, then generate answer, then generate answer to end. So there's just one node which is called generate answer, and this is its function. So what it does is, whatever is the question you ask, it will just answer you like this, with answering and then the same question. Okay, right now I'm not using LLM, but in fact you should LLM here. So what will be the output? If I ask what is Langgraph, then it will answer will be answering what is Langgraph. Right now we are not using LLM, so we will not get any answer. Okay, so why I showed you this? Okay, so let's go back to the slides. So this looks like a simple state dictionary, right? But under the hood, this question and answer are compiled into channels. Okay, and for plain fields like this, what I mean by plain field will be clear in next few slides, just in a few seconds you can say. Then Langgraph uses default last value behavior. So as I said, there are many behaviors, merge behaviors. So by default, it's a last value behavior. So last value means that whatever is the last value you will get as an answer. You will not see any other previous values. And if you are not building chat application, it's just simple question answering, then you will not see like whole chat history. It will be just most updated question that you ask and the most recent answer that you get for that particular question. Okay, so here this was plain thing. Okay, but reducer will be added somewhere here. Okay, and we will see subsequently. Now let me motivate why reducers are needed. So what happens if two nodes write to the same key in the same step? And this we have seen in the last class, in the parallel workflow, that both the nodes were trying to modify the same state, or you can say at that time it was same state. But what happens if we have the same key as well? Okay, so for example, this workflow. So this is very simple workflow of parallel. So there are two nodes. So it starts from A and B. So start goes to both A and B in parallel, and then A and B both goes to end. So just to compare, it's similar to this one. Just forget about this call LLM3 and this aggregator. It's just this much, start to A, start to B, and then both goes to end directly. Okay, this is very simple workflow like this. And what's the function of each node? It simply returns logs A ren and it says B ren. Very simple. I'm just keeping it lame right now. And if I build this, let's run this. And if I invoke, it will be an error. So now what error says? At key logs can receive only one value per step. Use an annotated key to handle multiple values. And this is where reducer comes into play. So let's go back to the slides. That okay, without a reducer, this key behaves like a last value channel. So parallel writes to the same key in the same step are not merged automatically. Okay, and that's why we are getting error. That because there is a parallel writes to the same keys in the same step. If it even if it's not simultaneously, it will work. But this was simultaneous because it was parallel workflow. So they won't be merged automatically. And that's why we are getting error, because why? The default behavior is last value. So now it will confuse, like, okay, which should I listen? Should I listen to node A or should I listen to node B? That's why we are getting this error. Here comes a reducer into play. That this is what reducer does. Rather than just, so what we did here was simply list of strings. We said that, okay, this is our type, state is our type dictionary, and logs key is list of string. But here we are using this annotated module from typing extensions. We are saying that, okay, you have to add. So, and obviously in logs, we need logs history, right? In any application, we need to debug, right? So we need history of all the logs. So we don't delete, or we just don't need the most recent log. We need all the logs. And that's why we need this operator dot add. So by default is last value, but if you specify like this, now the channel will know. So in fact, this is not the key behavior. This is the channel behavior. And as I said, key and channel are related. At runtime, key becomes the channel. Okay. And now if I run this, then you will see here, you are getting the appended output. So A ran, B ran, correct? So that was the reason. Now logs is not using simple last value behavior anymore, because we are using this annotated, and Langgraph compiled this key into an aggregated channel. So what you can say that reducer is not running inside the node, even though we are specifying inside the node, it runs when this Pregel applies all writes to the channel at the step boundary. So what does it mean by step boundary? Is the very last step. So Pregel runs into 3 phases, as I explained. So in the very last phase, this happens. Okay. So, and this is a very central runtime behavior from this Pregel model by Google. Now let's again revisit the complete flow. Okay. So firstly, node executes. Node returns the partial update. Pregel buffers updates for this step. Pregel groups updates by the channels. Then each channel applies its update logic. And then updated channel triggers the next node. Okay. So you can say that reducers are part of the channel update state. They are not direct state mutation. Even though we are specifying them here in the state, but they are not direct state mutations, but they are part of the channel update. Okay. So that's why suddenly this reducer came into play. Then again, as I said, I had a separate slide for channels. So what is channel? I already explained, but let's visit through a dictionary definition, or you can say book definition of channels. So channel is a runtime object that owns how a value is stored and updated. So as I said, there are many behaviors. Default is last value. Okay. But you can use like operator, which we used like add, you can accumulate. You can also use topic, used for more like pop some stream or multi-value message channel. So in one line, what is reducer and what is channel? You can say that reducer is a merge rule and channel is the thing that owns this merge rule. And that's how this reducer and channels are related. And channels doesn't stop here. There are something called as internal channels as well. So channels are not only for your business like messages or logs or states, which are just used for making applications. But Langgraph also uses channels internally for routing and execution, because so there is always routing going on, right? Because right now what Langgraph does is it executes one node, then there is another node, then there's another node. So there is, and it should route as well. Like, okay, if there's a conditional edge, you should also go to some other node, right? Rather than going to the very next node. Okay. So nodes are not really calling each other here. What is happening here is they are reacting to this something called as channel updates. If you will follow this link, is this one only. Let me try to open it. So what happens is here, yeah. So rather than like directly using this something called as high level API that we always use, like build nodes, add node, what we can do is we can also use directly the Pregel. Okay, so Langgraph also has this complete Pregel module. So what this does, this is also the same thing, but just written in a different way. So since it's a channel, you can say there are some wording called as actors and channels and subscribe. So what this does is, this is one of the node, and what this does is it just, this is its function, so it will just add. Okay, so what it will do, it will subscribe to A, so it will listen to A and write to B, you can say that. And how this works, so these are the channels. You can say A is channel, B is channel, and A is the input channel, B is the output channel. So what happens is, if we write F double O, what it will do is it will just add F double O, F double O, right? And that's how it works. So it's not like nodes are calling each other. Okay, they're just reacting to this channel updates, that this channel was updated, and what channel updates needs to do, it should write to this node. So then it will just write to this channel, right? So that's how this entire internal thing is going on. And so once you stop thinking of graph as a mutable dict or a dictionary and start thinking of it as channel based runtime, then this reducer, channels, everything becomes very easy to understand. Okay, so this was all about this internal working. There's still a lot. So what you can do is, like, you can go fully through this Langgraph repo. So there's an official repo from Langgraph, and you can go, like, for example, you can go to this graph. There is also something called as state.py, and this file has everything. So you can use any AI tool to like explain you very nicely and thoroughly. But you can go here and you can see, I'll explain you here few things. For example, this is the state graph that we're using, right? All the time. So how this works? So this is a reducer here. So firstly, state is a type dictionary. So we have seen this annotated list, and this is a reducer. We say that, okay, it should be operator dot add. And then this is the node. We define node like this. There is something also called as context, but we'll see this in one of the next video, or else this will be too much complicated or overwhelming for you guys. And that's how this entire internal thing works. Like Langgraph dot add node, we set the entry point, set the finish point, that how the compile thing works. So this is very simple. Here what's going on is you give input as 0.5, and the context is something, some you can say it's something that is always static. Okay, and what's going on here is you are just taking that 0.5, multiplying it with 3. So 0.5 into 3 is 1.5. Okay, half of 3 you can say, and then 1 minus 0.5, which is also 0.5. So you are again doing the half of 1.5, which is 0.75, and you can see we are getting 0.75 as the answer. Okay, so this is how the simple flow, and you can check that it has all the methods here. Okay, like state has all the methods, like add node, add edge, all methods are here. And similarly, you can also check the channels. So if you check here, there should be something called as channels, and you can see this is the default behavior that I just explained you. That is the last value behavior. But there are other behaviors as well, like binary operations based behavior, any value behavior, ephemeral behavior. I hope I pronounced it nicely. But you can go through all of this. This is the like official repo. I just cloned it on my PC. Okay, so I hope this brings some value to your Langgraph journey. And again, of course, like in next lecture, we will continue with our conditional workflow, where we had actually wanted to do, but we just did this one. Thank you.